Happy Cinco de Mayo, cadets. This is lesson 34. It is our second half of the introduction to separations in which we're going to focus on band broadening. Please remember that today your formal report is due. This is the determination of the pKa of bromocresol green. So please upload that document to Teams, and if you have any difficulty, please contact Captain Friday and/or myself. Today we're going to focus on what is known as band broadening, and that has to do with the width of the peaks as they come off the end of the column and the implications towards the resolution of separations, the contributing factors to band broadening, and how we go about optimizing the flow rate of our mobile phase. We'll end with a summary of everything we've learned about the fundamentals of chromatography and the different parameters we use to assess the effectiveness of that separation and our optimization. When we do column chromatography, we have a choice of which method to use. We can do high performance liquid chromatography, in which our mobile phase, as the name implies, is a liquid. Or we can do gas chromatography, in which our mobile phase is a gas. So which one we might prefer to do depends on the nature of our sample. To do gas chromatography, you must also place your analyte species of interest that you're trying to separate, all of the analyte species you're trying to separate. You must put them up into the gaseous phase. You must volatilize them. This is not possible with some large molecules that have high boiling points, and it is also not desired if we are dealing with molecules that degrade when we subject them to high temperatures. Okay, so GC is an easier method to use. We'll talk more about this later. So if you have a choice, you want to prefer to use gas chromatography. But if you're dealing with thermally sensitive materials or those that have a high boiling point, you are going to do liquid chromatography. And the latter is the preferred format of separations for biochemical research, where we're dealing with those kinds of sensitive compounds that are either large in nature or degrade with temperature. So the columns that we use for these two techniques are as follows. When we do LC, we are using a packed silica column most often. Okay, as we talked previously, these are silica particles, spherical in nature. Okay, and we've bonded to the surface a desired stationary phase material that has a property which is going to work well for our separation. In the packed columns, the spherical particles pack very efficiently, and we want to minimize the size of the particles to also enhance a number of things: the surface area of the stationary phase, as well as the efficiency of the packing. If we do gas chromatography, we have a choice of columns. We can do a packed column similar to that in LC, or we can choose what is known as an open tubular column. Okay, the open tubular columns, as the name implies, your mobile phase is going to flow down the center of an open tube. There's going to be little resistance, and that's going to happen easily. The types of the open tubular columns are as follows. We have those in which we coat the stationary phase material here in the light blue on the inner surface of the open capillary tube. These are called capillary columns. So there's your stationary phase material. That is a wall-coated open tubular design here, wall-coated. Okay, if we want to increase the surface area of the stationary phase, we might place onto the surface little silica particles. So in a porous layer design, we have placed little silica particles onto the surface. So this is the porous layer, open tubular column. And once again, by placing porous silica particles, we are increasing the surface area and the capacity of the column. And finally, support coated open tubular. That one okay, these columns have the little silica particles onto which we have placed a stationary phase material. So these are the different options with open tubular design. The important thing I want you to recognize, a couple things, with the resistance to flow, okay, in terms of a mobile phase trying to flow over a packed column when that mobile phase is a liquid, there's going to be a huge resistance to that flow. That's why we have to use high pressures. We have to use pumps to get a liquid to flow over a packed bed. So in those instruments, we're going to have pumps to push the mobile phase over the packed column. In GC, okay, our gas flows a little easier over a packed bed. And also, if we're using capillary columns, there is no resistance to the flow. The mobile phase moves easily through the open center of the capillary column. When carrying out column chromatography using HPLC, our columns are typically a packed silica column. And historically, LC was not even a possibility for many years because of very poor resolution of the peaks as they came off the end of the column. And that was due to the fact that in the olden days, the silica particles were of an irregular shape. They did not pack efficiently into the column. And we had real big peaks that came off the end, and we had a lot of overlapping problems. So LC became a competitive technique when industrial manufacturers were able to manufacture the silica particles that were spherical in diameter so that they packed efficiently and their diameters were small. And the diameter of the particles are measured in microns. So we have illustrated here different silica particles starting with 30 micron diameters and then 20 micron diameters and 10 over here, 5, 3 micron diameters, and you can now actually acquire columns packed with silica that are all the way down to 1.7 microns. So the smaller the diameter of the particle, the more efficiently it packs, the higher the pressure you need to force the flow of the mobile phase over the column, but the smaller the particles, the greater the surface area. So there's a lot of advantages to having small, very spherical silica particles. A huge decision one has to make is the length of the column you're going to use in a separation. So the length of the column is going to dictate, obviously, how many particles there are. Okay, that's going to have an impact on the capacity, how much sample you can put on the column. Okay, it also will impact how long it takes for a separation to occur, etc. And remember, the more stationary phase you have, okay, so increasing surface area gives increasing amount of the stationary phase material that you have. That increases your capacity, your ability to separate structures that are very similar in nature structurally. So the length of the column, and we usually measure this in centimeters or millimeters, is going to impact the separation in many different ways. So let's revisit the parameter of column efficiency as measured by the number of theoretical plates. Remember, this is the number of exposures that a molecule will have to the stationary phase and the mobile phase as it traverses the column. If you will recall, we have an equation in which the number of theoretical plates is measured by 16 times the retention time squared over the width of the peak squared. And we can express that equation in a similar fashion if we want to measure the width at half height of that peak. So the important thing to remember is that to have a good resolution, we want to maximize the number of theoretical plates. As we increase n, we enhance the resolution. This is mathematically expressed in the equation below. So resolution is actually proportional to the square root of the number of theoretical plates. The other term in this equation, this gamma, is the unadjusted relative retention between two components. So if we had a separation happening, such as the one we see at the left, the retention time A is that of the component that takes longer to get off the column, and in the denominator is the retention time of the species that comes off faster. Okay, so resolution is directly proportional to the square root of the number of theoretical plates. If we want to have good resolution, and remember to have a clean separation, that value has to be a minimum of 1.5. So resolution has to be bigger than or equal to 1.5. So we want to maximize the number of theoretical plates. So in the equation of the theoretical plates, though, notice that the width of the peak is in the denominator. So if we increase the width of the peak, if we have broad peaks, that decreases the number of theoretical plates. If we decrease the number of theoretical plates, we limit our resolution. And in a practical standpoint, what that means is broader peaks are going to have a greater tendency to overlap, and we won't have that clean separation. Illustrated here is what happens to the width of a peak at different points in time as a species traverses the column. So at time 1, early on, you'll notice that we've got two components there. So here is the width of the B peak early on. So it is, it's maybe this wide. So this is the width at time 1 for B. Later in the separation, further down the column, peak B is going to look something like this. All right, so the width of B, as it moves down the column, it gets wider. So the width of B down here at time 2 is bigger than the width of B at time 1. And the same is true for A. So the problem with peaks broadening is that there's a greater chance for overlap, and we may not have the resolution we need in our separation. So as we carry out a separation, we hope to minimize the band broadening of the peak, and that is the measure of the peak width. One thing to recognize is the parameter of diffusion is what controls the width of the peak. There is a natural tendency of a species to move from a region of higher concentration to lower concentration. And so the more time that a component spends on the column, there's going to be this natural tendency for the molecules to take different amounts of time to get off the column. The parameter that is a measure of the band broadening, the width of a peak as it comes off the end of the column, is called the theoretical plate height H. That is the parameter that we use to measure band broadening. The illustration on the left shows you what happens to the peak over time. So when we start, you eject your sample and all of the molecules of a particular kind are kind of starting off at the same place at the same time. The longer those molecules spend on the column, increasing time as we move down the column, diffusion occurs. This is the natural tendency for the species to move from a region of high concentration to lower concentration. So the bandwidth gets wider. And by the time we get to the end of the column, that width is even bigger. Okay, so that's something that we simply can't control entirely, but we want to optimize our separation to minimize the band broadening. And we measure that with what we call theoretical plate height H. So how that parameter relates to our efficiency is as follows. We define our theoretical plate height as follows. If n is the number of theoretical plates, we calculate H as the length of the column divided by the number of theoretical plates. So if our column is so many centimeters long, okay, then we're going to divide by number of theoretical plates. And so the units on the plate height is going to be centimeters per plate. So remember that to optimize resolution, that's the ultimate goal of the separation. We want our resolution to be maximized with a minimum of 1.5 to have a clean separation. To optimize resolution, it is proportional to the square root of the number of theoretical plates, which is inversely proportional to the length of the column over the plate height square root. So what parameters influence the extent of the band broadening that occurs as a group of molecules traverses the column? So there's three sources to band broadening: mass transfer, eddy diffusion, and longitudinal diffusion. We're going to start with eddy diffusion. So eddy diffusion is the flow via multiple paths. So once again, if you consider a packed column of silica particles such as illustrated here, and this one illustrates particles that are not spherical, so you can see the problem that it's going to create for different paths. Okay, so we have a distribution of molecules of the same species coming into the column. Okay, so the first molecule is going to experience this path as it flows through the column, and it's going to come out early. In terms of time, it's going to come out right here, time 1. It's going to be the first one to get through the column. Molecule number 2 takes a different path. It flows through this packed bed and it kind of meanders a little bit. If there's a lot of void volume between these particles, there's going to be different options for how long it takes a molecule to get through. So molecule number 2 is going to take longer than molecule number 1. And then molecule number 3 is going to experience a different path. And it's going to do a lot of meandering between these particles. And it's not going to come out until here. So the more variability there is with the paths that molecules can take, the broader is the band. So the equation that contributes to the plate height, the band broadening, okay, there is a contributing factor that comes from eddy diffusion. It is expressed by this equation here. The contribution we're going to just symbolize as A. And it's going to depend on two parameters. Okay, a lambda, which is simply, it's a constant that depends on the efficiency of the packing of the particles in the column. We've illustrated here what happens with an irregularly shaped particle. The reality in modern days is that we're going to use spherical particles that pack much more efficiently. The more spherical they are, they pack very efficiently. So we're going to get more consistent flow and possible paths of flow if we have spherical particles that are of the same diameter. So that second parameter in the equation is the diameter of the particle. So obviously, as you decrease the diameter of the silica particles, you're going to decrease the magnitude of the contribution to band broadening from eddy diffusion. And if you decrease that, you decrease the plate height. And that means you're going to enhance your resolution. So once again, historically, LC was not even an effective method until industrial manufacturers could start producing these silica particles with a spherical morphology and very small particle diameter. The second factor that contributes to band broadening is what we call mass transfer, or this is also referred to as equilibration time. This one comes from the fact that it does take finite amount of time for a molecule to move within the mobile phase and the stationary phase, and in between the mobile phase and the stationary phase. So once again, if we had a silica particle and there's a stationary phase material on the surface, and our molecule is out here in the mobile phase. Mobile phase is out here. Okay, so it's going to spend some time moving within the mobile phase. And then it's going to come into the stationary phase. It's going to hang out in the stationary phase and move around for a little bit. And then it's going to come back out into the mobile phase, so on and so forth. So we can equate the contribution to the band broadening coming from the mass transferred to and from the stationary phase and within the mobile phase. So these two equations express the dependence of band broadening, our plate height coming from mass transfer. Okay, the top one deals with the stationary phase and the parameters that we have here. This function of the capacity factor, okay, so that is the K value that we learned about before. This term right here, d sub f squared, so that has to do with the thickness of the stationary phase film on our surface. So up here, if this is our stationary phase film, that is the thickness of the stationary phase film. And in the denominator is our diffusion coefficient for our particular species within the stationary phase. And the last parameter here, so this factor that contributes to band broadening, the plate height, is directly proportional to U, that is the flow rate of our mobile phase in mils per minute. In a similar fashion, the contribution for mass transfer within the mobile phase is the equation below. Okay, there is a dependence once again on some function of the capacity factor. This one is directly proportional to the square of the particle diameter, once again an important parameter. And in the denominator is the diffusion coefficient of our particular species within the mobile phase. And this parameter is directly proportional, once again, to the flow rate of our mobile phase. The final contributing factor to band broadening is longitudinal diffusion. Diffusion is a spontaneous process and it's random in nature. So as our mobile phase is flowing over our packed bed in the direction of the arrows, when a molecule diffuses, it can diffuse in any possible direction. So there's an equal probability of it diffusing, if my molecule is, let's say, here, it could diffuse in the same direction as the mobile phase, or it could diffuse in any other direction, okay, which includes a direction which is 180 degrees opposed to the direction of the flow of the mobile phase. Obviously, if a molecule moves in that direction, okay, the molecules ahead of it are going to come out sooner. So that is the impact of longitudinal diffusion. The mathematical dependence of this factor to the plate height, h, is expressed according to this equation, which is going to be inversely related to the flow rate of our mobile phase. In the numerator of this equation, we have a constant that once again depends on the efficiency of our packing, so don't worry too much about that. And this one is proportional to the diffusion coefficient of our particular molecule in the mobile phase. So unlike the previous two influences on the band broadening and the plate height, this one is inversely proportional to the mobile phase flow rate. So this slide simply illustrates the impact to the width of a band that comes from mass transfer and longitudinal diffusion. On the left, you see that at one point in time, the position and distribution of your molecules might look like this. That's your bandwidth, okay? But if you have a slow mass transfer or slow equilibration time in the different phases, okay? So if out here is the mobile phase and down here is the stationary phase, okay? If the molecules within the mobile phase are moving faster than in the stationary phase, the molecules in the stationary phase are going to get behind. So you can see this time frame in which these molecules are lagging. And so the total bandwidth now is big due to mass transfer events. And you can see the before and after. So the width was more narrow up here. After some time, it gets wider as it traverses the column. The impact from longitudinal diffusion, so if we are at an earlier point in time, this is the width of our band. Okay, let me redo that. This is the width of our band right here. But once again, after some time, and as the molecules, the slug of molecules moves down the column, once again, some of the molecules are going to have a tendency to move in the opposite direction to the flow of the mobile phase, which in this case, the mobile phase is flowing in this direction. So at some other point later, the band of my molecules is much wider because some are getting left behind because they move in the opposite direction of the mobile phase just due to the spontaneity of the diffusion process. So taken together, the three contributing factors to the band broadening collectively make up the Van Deemter equation, which shows us that the plate height, which is the chromatographic parameter, which is a measure of the band broadening, has three contributing elements. Eddy diffusion, that comes from multiple flow paths. Then we have longitudinal diffusion, moving in the opposite direction to the mobile phase. And then we have mass transfer, or equilibration time. So from a mathematical perspective, eddy diffusion has no dependence on the flow rate of our mobile phase, whereas longitudinal diffusion has an inverse relationship, and mass transfer has a direct proportionality. So we are combining three different mathematical functions to get the overall plate height as a function of the mobile phase velocity. So the Van Deemter equation, okay, so the eddy diffusion here is independent of the flow rate. Longitudinal diffusion is inversely related, so you get this exponential decay, and mass transfer is linear. So when you combine all of those three things, you get what we call a Van Deemter plot, which characteristically has this shape. And how the Van Deemter plot is useful is we want to optimize our separation. We want to find out what is our optimal flow rate so that we get the narrowest bands and the best resolution. So to find the optimal mobile phase flow rate, we want to look at the plot of the mobile phase velocity versus our plate height h on the y-axis. Okay, we are looking for where the band broadening is smallest. Okay, smallest plate height is there. So this is our optimal mobile phase flow rate. This is an important parameter that one has to choose when carrying out a separation. So to summarize, when we carry out column chromatography, okay, we want to minimize the band broadening. And keep in mind, if you're doing gas chromatography, you have a choice of the kind of column you're going to use. You can use a packed column, or you can choose an open tubular column, a capillary column. So it's important to know how these two different columns perform. So what you're looking at is a comparison of separation of specific molecules by GC carried out at a constant temperature. Okay, and how do these two columns perform, the packed versus the open tubular, with regard to a number of parameters? So first of all, the length of the column. Okay, if we're doing a packed column, in this particular application, okay, the length of the column is 2.4 meters. So once again, this is GC, not LC. Open tubular columns are incredibly long. The outer casing is a thin metal, and what they do to make it efficient and fit in the instrument is they wind this thin metal time and time and time again, and so it sits efficiently in the instrument. The linear gas velocity, okay, 8 centimeters per second for the packed, 16 centimeters per second in the open tubular. As you might anticipate, getting a gas to flow over a packed column, there's going to be a little bit more resistance, so it's not as fast. The plate height, so once again, this is the measure of the band broadening, and we want to look for, to optimize resolution, we want this to be as small as possible. So for a packed column, it has a 0.73 millimeters per plate, and in the open tubular, it's smaller, 0.34 millimeters per plate. Therefore, we get better, smaller peaks. So comparatively, if a peak coming off the packed column looked like this, the peak coming off the open tubular is going to be more narrow and less prone to overlap with another species. The retention factor K, okay, that has to do with how much stationary phase material is on the column, and with a packed column, this is a much bigger parameter. It's 58.6 versus an open tubular 2.7. Okay, once again, if you have packed particles and they're porous, and we have stationary phase on the surface and down in the pores, we're going to have a lot more surface area of stationary phase material versus if we have an open tubular column where the only stationary phase is whatever we can get on the inner surface as that mobile phase flows through that open channel. So we have a much greater retention factor. Capacity factor is the same thing on a packed column versus an open tubular. Theoretical plates, here's a huge difference. The theoretical plates for a packed column, 3,290. Comparatively, for open tubular, 294,000. This is where open tubular columns deliver superior resolution. Superior resolution coming from very small h. We get very minimal band broadening when we're going through an open tube, which means we're going to have large number of theoretical plates, and we are going to get the best resolution. And that is our next measure. So resolution on the packed column, we barely make clean separation, and on the open tubular, much greater. And then retention time. So retention time typically has to do with the flow rate of the mobile phase and how much time your sample spends in the stationary phase, which has to do with how much of that stationary phase is present. So in this case, you'll see that the retention time of the packed column is 29.8 and the open tubular is 38.5. So in summary, if you want to get the best resolution and you can do gas chromatography and sample capacity is not a problem, you're going to want to choose an open tubular column. It's going to give you the most ideal resolution. However, if you've got components that require greater capacity, that is the retention factor, okay, you're going to want to choose a packed column. So our final slide of the day is simply a summary of all of the important chromatographic parameters that we measure and interpret when we carry out a sample separation using either gas chromatography or liquid chromatography. So this is just a summary of all the important things we talked about: the partition coefficient, retention time and adjusted retention time, okay, the retention or capacity factor and how it's measured off of your chromatogram, the selectivity factor between two components, the unadjusted relative retention, gamma, which is down here in our resolution equation, the number of theoretical plates, the plate height, and then measuring resolution directly off of a chromatogram by looking at and measuring the retention time and the peak width. So this ends our introduction to separations and the fundamental aspects of carrying out a clean separation. And the next lessons are going to focus specifically on the methods of HPLC and GC. Thank you for listening.